So hello, welcome to another class. Today we're going to start up not start up, we're going to continue this chapter. We're going to talk about chemical bonds, the penultimate chapter, if you will. Um, here's a video that actually explains the different types of bonds, but I'm not going to play it in class, but you can watch it if you want, since this PowerPoint is online. But I do have something I want to talk about before we start, and that's the final. The schedule for the final exam was finally posted, as I emailed you. I guess that was yesterday. I actually posted the entire final exam schedule for all classes, just in case people want to see it. But your final is on Monday, May 10th from 12:30 to 2:30. Or at least that's the official time slot. I will leave the final open till 2:45 to give you an extra 15 minutes to upload. If anyone has issues with that time or something going on, let me know. We might be able to work something out. But that is when the final is. Monday, May 10, 12:30 to 2:30. It's of note, my other final, because I have two classes, is from 3 to 5 on Monday, which means I said I was going to try to have everything graded by the next day, but I have both finals on the same day. So worst case scenario, you might not get grades till Wednesday, depending on the order I grade both classes, since both classes are same day. Um, I did upload last semester's exam. I'm not going to go over it in class, but as I said before, I'm going to do an extra session at some time. I sent a poll. That is the wrong version of poll in that right there. I sent a poll on when is good. Um, I want to see what people say, but either way, I will record the video and put it up. Um, Actual structure for the final, I haven't actually said that in class yet, so I figured I should. Um, the final is going to be 40 questions long, 8 pages of problems. You've had 4 pages of problems on every other exam. This one is twice as long, but it's more than twice as much time. First page will be chapter 9, second page will be chapter 10, third page will be chapter 11, fourth page will be chapter 12, and the remaining 4 pages will be everything else, with the next page being 1 and 2, the page after being 3 and 4, the page after being 5 and 6, and the page after being 7 and 8. So for chapters 1 through 8, there will be either 2 questions or 3 questions per chapter. Questions 9 through 12, there'll be 5 questions per chapter. So, any questions about the final before I move on? Okay, we've been talking about ionic bonds and ionic compounds. So now let's learn how to work out an ionic compound. I ended on this slide. This slide is nothing new. I'm just going to put it up there to review. That when you have an ionic compound, the metals give away electrons that become positively charged, or cations. The nonmetals take electrons, become negatively charged, become anions. And when they join together, the total charge must be 0. But the way to really work out the charge of an ionic compound, well, that's the way to really work out. The way to practically work out an ionic compound, the easy way, is what is called the crossover method or the diagonal method. Anytime you want to write a ionic compound, it says chemical here in general, but really just an ionic compound, I recommend doing this. If you are given an ionic compound, write down the names of the ions with their charges. So if I say we have sodium chloride, that means we're mixing the sodium ion and the chlorine ion. Now the sodium ion has a charge +1 because that is where it is on the periodic table. It's in family 1A. Chlorine has a charge -1 because it's a nonmetal in group 7, so charge -1. If I want to write the compound, what I'm going to do is I'm going to grab the superscripts and drag them subscript to the other element. Okay, I'm going to take this one and drag it down there. I'm going to take that one and drag it down there. Na1Cl1. You don't normally write ones, but I'm just trying to make a point. Note I don't keep the charges when I do this, because this is a quick hand thing. But this will help when it's not so simple. Take, for example, aluminum chloride. Aluminum has a charge +3. That's because aluminum, which is right here, is a metal with 3 valence electrons. What that means, if I want to find the formula for aluminum chloride, I'm just going to take that 3 and drag it down in front of the Cl. I'm going to take this 1, or behind the Cl. I'm going to take this 1 and drag it after the aluminum. The chemical formula for aluminum chloride is AlCl3. That is how you can work out ionic bonds. Any questions though? Of note, this does work with polyatomic ions. Sulfuric acid is HSO4. I can do the same thing. I can just take this 2, drag it down to the H. This 1 drags down to the SO4, which will affect the entire SO4. To give you a very complicated one, ammonium sulfate. Ammonium has a charge +1. Sulfate has a charge -2. If I want the formula for ammonium sulfate, I'll take this 1 and drag it down. It skipped the arrow for some reason. I'll take this 2 and drag it to the NH4. But it's to the entire thing. It gets parentheses around it. One more, calcium phosphate. I take this 2, drag it down to the PO4. Take this 3, drag it down to the calcium phosphate. Any questions though? This is going to be important. You're going to need this a lot for this chapter and next chapter. Okay, there is one exception. If both, the plus sign shouldn't be there, if both compounds have the same, you reduce. Let's say you have magnesium oxide. Magnesium has a charge +2, oxygen has a charge -2. If I use this cross method, I would drag this 2 down to magnesium. I would drag this 2 down to oxygen to have Mg2O2. Anytime both of the numbers are the same, reduce it. Just say MgO. The same logic for both 3. Aluminum nitride is just AlN, not Al3N3. Really, in general, you should always reduce if they have a common denominator. So something like Pb4 and O-2 becomes PbO2, right? If both numbers can be divided by something, you should. Although this case here will come up practically never. But it's worth noting that that is a case. Okay, any questions? So yeah, in an ionic compound, it's always the positive metal ion or the negative non-metal ion, or the cation and the anion. Overall charge is 0, just use this cross method. If you're dealing with transition metals that can have a different charge, what you'll do is you'll write the structure just using this cross method. Fe iron 2 oxide is FeO because iron 2 has a charge +2. Iron 3 oxide is Fe2O3 using this cross method. Also, always make sure you put your cation before your anion. O3AO2 is not correct. It's AO2O3. Oh, sorry. I hope I said this before we started. I don't know who was on, but allergies are. I opened up the windows of the house because it's nice outside, and I just feel my nose filling with the allergies. So we'll see how I go throughout this class, and whether or not I die into a quivering mass of allergy, sinus, and congestion. Okay. Let's do one more example from scratch. Let's say I ask for the compound between Sr and S. Well, Sr is strontium, found right here. Strontium is in family 2A. Therefore, when strontium ionizes, it's a metal with two valence electrons. Therefore, when strontium ionizes, it gets a charge +2. S is sulfur. Sulfur is a nonmetal with 6 valence electrons. That means when it ionizes, its charge is 6 minus 8, or -2. So with strontium and sulfur, we're mixing strontium with a charge +2 and sulfur with a charge -2. Therefore, to find this compound, I'll just do this cross method. I'll take 1, 2 and drag it down. Take the other 2, drag it down to get SO2S2. However, they're both the same, so I reduce it. That is strontium sulfide. Okay? Okay. That's ionic bonds. That's everything you need to know for ionic bonds. I'm going to spend the rest of today, which is most of today, on covalent bonds. Now, ionic bond is anytime a metal mixes with a nonmetal. Metals give away electrons, nonmetals take. But sometimes you have a non-metal bond with a nonmetal. And this is kind of weird because nonmetals only take. And if they both only take and no one gives, well, that kind of sucks for everyone. But here's the thing. What happens when you have a nonmetal with a nonmetal is instead of a give and take relationship, they share. That they say, I want this electron, you want this electron. Metals and nonmetals is, I don't want this guy, you want it, I'll give it to you. But this is, we both want it, why don't we just share it? Both use it. Split it between us. What it is that each element uses the available electrons to complete their octet. Or in the case of hydrogen, they're 2 electrons. Carbon dioxide, for example, oxygen starts with 6 valence electrons. Carbon starts with 4. And carbon shares out its electrons, borrowing 2 from each oxygen and letting each oxygen use its 2. Now, this is kind of interesting. This is when it sounds like I'm going to be personifying things, though I don't mean to. It's going to sound a lot like really sappy life lessons, but the process of sharing electrons makes it a stronger bond. When it's just give and take, it's not a very strong bond. But when you're sharing and everyone's using it, it makes them literally closer together and a stronger bond. It's very hard to break covalent bonds because sharing brings you closer together. Yeah, really sounds like sappy life lessons, but this is what actually is going on. Now, in a normal covalent bond, the shared electrons are what is called delocalized. This means they're shared evenly throughout everything. Take, for example, hydrogen chloride. Hydrogen is a nonmetal with 1 valence electron. Now, hydrogen's weird. Hydrogen only wants 2 electrons total. We've talked about that before. But chlorine has 7 valence electrons. What happens when you have hydrochloric acid is hydrogen shares its one and only electron. Chlorine shares 1 of its electrons. And what that gives you is the hydrogen has the 2 electrons because the hydrogen has both of these 2. And the chlorine has 8 valence electrons because it has both of these 2. The hydrogen becomes isoelectric with helium. The chlorine becomes isoelectric with argon. Everyone is happy. Now, this does mean in a covalent bond, you are overlapping your energy levels. This is why they are literally closer together. The ionic bond is just this guy, they kind of butt up against each other. But a covalent bond, they have to overlap their energy levels, and what happens is they kind of merge. They get shoved together. They overlap. In fact, in ionic bond or a covalent bond, you can measure what's called the bond length. The bond length is the distance from the center of one atom to the center of the other. And in a covalent bond, the bond length is always less than the individual radii. What I mean is, take, for example, that hydrochloric acid. Hydrogen has a radius of 0.037 nanometers. You might notice that does not agree with the value I gave for the Bohr radius. That's a whole other can of worms. We can come back to that. Chlorine has a radius of 0.099 nanometers. But when you have hydrochloric acid, their radius is 0.127 instead of 0.136 because they're not just up against each other, they're shoved into each other and merged. Sharing brings you closer together. Okay. Also, as I said, it takes a lot of energy to break these bonds. That if you want to break a covalent bond, you need to put in energy. Now, that is also true for an ionic bond. To break an ionic bond, you need to put energy in. But it's very easy to break ionic bonds. It takes a small amount of energy. It takes a lot of energy to break a covalent bond, where the energy required to break a bond is called the bond energy. And in fact, when a covalent bond is formed, it releases heat. If you take hydrogen and chlorine gas and turn them into hydrochloric acid, it produces heat because it's conservation of energy. It's going to have extra energy because it has less energy mixed together. And actually, we'll get into this next chapter a lot with energy of breaking bonds and forming bonds and all that. That's really a topic for next chapter. But it is note that there was a lot of energy at play when breaking and making bonds. Also, a regular bond, or a single bond, if you will, is two shared electrons. And if you look at the hydrochloric acid that I showed earlier, hydrogen shared one electron, chlorine shared one electron. That is a bond. There is also such a thing as double or triple bonds. If in a bond 2 electrons are shared, that is a double bond. If in a bond 4 electrons are shared, that is a double bond. And if 6 are shared, that is a triple bond. You'll never go higher than triple. In fact, each element can have a max number of bonds equal to 8 minus the number of valence electrons, except for hydrogen. Hydrogen can only form 1. And this means, but when I say this, that is treating only how many singular bonds. One double bond counts as 2 singular bonds. One triple bond counts as 3 singular bonds. And so what that means is, for example, nitrogen, who has 5 valence electrons, can form 3 bonds. That means nitrogen can form 1 triple bond, or 1 double bond and 1 singular bond, or 3 singular bonds. Now, this would be very, 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 very useful if we were going to do the last lab, which, as in the lab that we were not doing, it's not there. You never have seen it. It's because it's a lab that only really works in person. I couldn't make it work on a video, so I got rid of one about bonding. You won't need to worry about how many bonds you can make, except in that lab that you are not doing. What you can worry about, though, is what a molecule looks like. You see, we can use this bond idea and work out exactly what any molecule looks like using what is called Lewis structures. What a Lewis structure is it's also called an electron dot formula. It's just you draw an element and surround it by how many valence electrons it has. You just take an element and say, and yeah, draw dots. Carbon has 4 valence electrons. If I draw carbon, I put 4 dots around it. And that's just for individual atoms. You can do it for compounds. That for a compound, we would just draw how many electrons are shared. Any electrons that, yes.
I don't know if this was already discussed because I just joined, but what is a covalent bond?
Yeah, it was already discussed. Short version is a covalent bond is a bond between 2 nonmetals.
Okay.
And when it's a bond between 2 nonmetals, they share electrons instead of give and take.
Got it.
Okay. Now, in any electrons that are being shared are called bonding electrons. Other electrons that are not being shared are called non-bonding electrons. It's a pretty simple thing. Bonding, but if they're bonding, they're bonding. If they don't bond, they're non-bonding. We're not going fancy here. And what it is you can draw compounds. Doing the electron dot formula, you can keep track of the electrons and figure out exactly what the molecule will look like, some of its properties, and also whether the compound can even exist. The trees are trying to kill me. Now, I'm going to walk through the process of doing what I was just hinting at. And I'm going to kind of give an example and explain it as I do it. But I'm going to give a ton of examples. This, like the lens diagrams, I think is a lot easier to see in practice than to hear it written out how to do it. So let's say you have a compound and you want to know what the electron dot structure of that compound is. The first thing you should do is count the total number of valence electrons. And you just say, what is the total number of valence electrons in this molecule? It will always be an even number. Take, for example, water. Water is H2O. H2O. If I look at a periodic table, hydrogen is in family 1A. Because it's in family 1A, hydrogen has 1 valence electron. Oxygen is in family 6A. Because it's in family 6A, it has 6 valence electrons. No, I don't give a shit about its charge. Charge is only ionic compounds. We can ignore that. But I'll just say hydrogen has 1 valence electrons, oxygen has 6. But it's H2. There's 2 hydrogens. So 2 hydrogens means 2 valence electrons. Oxygen has 6. Water has 8 valence electrons. What you then do is you stop giving a shit at all how many valence electrons everyone started. You only care how many valence electrons everyone started with for this number. After that, it's going to be everyone gets 8, except for hydrogen, which gets 2. Say oxygen started with 6, don't fucking care. Oxygen gets 8. If you had sulfur, it gets 8. If you had carbon, it gets 8. If you had nitrogen, it gets 8. Once you count the total, everyone gets 8 except hydrogen, which gets 2. And what you should do is start by drawing the center atom. Now, I will always bold or underline the center atom for you because I'm not going to get into how you know what it is. But you're going to pick the center atom and surround it with 8 electrons. Everyone gets 8. And you should do it in pairs of 2. You then go and add on the other pieces. You add on the other elements, in this case, hydrogens. And then you'll make sure you have enough electrons that everyone gets 8, except hydrogen. And you'll move them however you need to do this. I'll show you an example, a complicated one in a second. Now, it's of note, any electrons that are between 2 elements, those are your bonding electrons. You can draw them as dots, but more commonly they're drawn as lines. Then I'll take my one in the bottom left and turn it into the one in the bottom right. To show this is the bond, I'll put a line there instead. So let me show you one in more detail and a more complicated one. Let's look at sulfur trioxide. Sulfur trioxide is a sulfur and 3 oxygen. I underlined the sulfur. That's because that's the center atom. Once again, I'll always underline it or bold it. And what I can do is I can pull out a periodic table and say sulfur trioxide consists of sulfur and oxygen. Now, sulfur and oxygen are both in group 6A. That means sulfur and oxygen both have 6 valence electrons. Therefore, the total number of valence electrons is 24. I have 6 from sulfur, and I have 18 from oxygen, because 6 times 3 is 18. Make sense so far? Now that I know I have 24, that's all that matters to me. 24 valence electrons. And I was to go and I would say, okay, sulfur is the center. I'll put a sulfur on the page and say sulfur gets 8 electrons. Why 8? Because everyone gets 8 except hydrogen. I don't care what started with 6. Everyone gets 8 but hydrogen. And I'll say, I'll give this sulfur 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Once again, drawing them in pairs of 2. I'll then say, okay, we have 3 oxygens. Let's just drop those on. And I'll put an O on each side. 3 of them. Now, here's the thing. Your total number of valence electrons has to be correct. We had 24 valence electrons. We used 8 valence electrons. That means we have 16 valence electrons we didn't place. And what you do is once you have the center atom happy, and once you added on the various elements, you will add the remaining valence electrons, and you'll add them wherever you need to so that everyone gets 8. And I'll just say I got 16 left. Once again, always make sure you have the right number of valence electrons. We had 24, I can only use 24. So my 16 left, I'll say 1, 2, 3, 4, 5, 6. That oxygen has 8. 7, 8, 9, 10, 11, 12. That oxygen has 8. 13, 14, 15, 16. There we go. 24 valence electrons. My sulfur has 8. We're happy. My oxygen has 8. We're happy. My oxygen on the right has 8. We're happy. My oxygen on the bottom has 6. Fuck that noise. It's not happy. It needs 8. That's a problem. The bottom O doesn't have 8 electrons. When you do this, if after you distribute the electrons, if you use up all the electrons you got, I used up all 24, and someone doesn't have 8, except for hydrogen, which only needs 2, you can form a double bond. What you should do is take electrons from the center atom. It'll always be from the center atom. And take electrons that are not in a bond in the center atom. These two right here are helping sulfur and no one else. I can't take them away from sulfur. If I take them away from sulfur, sulfur doesn't have 8 anymore. But I can move them. If I move them down into the bond, sulfur still has them. Sulfur still has 8. But now the oxygen also has them. That oxygen also has 8. And you can see this oxygen has 8 dots, has 8 valence electrons. This sulfur has 8 dots. It has 8 valence electrons. This oxygen has 8 dots. It has 8 valence electrons. This oxygen has 8 dots, has 8 valence electrons. That is the compound. Now, it's of note, bonds can be drawn as lines. Not going. So that would be the same as this. And that's the structure of sulfur trioxide. Questions? Now, a question I do sometimes get is, why did I say the double bond was that oxygen? It doesn't matter. It doesn't matter where you put the double bond. These are all the same thing. Officially, they're called resonance structures, but they're the same thing. I don't care which one you put the double bond on. Okay? We good?
Yep.
Let's do another. HCN, hydrogen cyanide. That's what it's called. We didn't get into things with 3 elements, how to name things with 3 elements when they're nonmetals with nonmetals, but just trust me, this is hydrogen cyanide. So hydrogen cyanide, I got to start by counting valence electrons. And I say we have H, we got C, we got N. H is in family 1A. It has 1 valence electron. C is in family 4A. It has 4 valence electrons. N is in family 5A. It has 5 valence electrons. So the total number of valence electrons is 1 plus 4 plus 5. 10. So I have 10 valence electrons. I'll start with my center atom, which is C, because I underlined it. And I say, C, it's an element. It wants 8. It gets 8. 1, 2, 3, 4, 5, 6, 7, 8. And I'll add my other things, H and N. Now I had 10 electrons. I used 8. So I got 2 left. And I know the goal is everyone gets 8 except for hydrogen. You see, hydrogen only needs 2. My hydrogen is content. My nitrogen is not. So I say my 2 remaining electron, nitrogen wants more. Let's give it to that. 1, 2. And there we go. There's all my electrons. My hydrogen has 2, it's happy. My C has 8, it's happy. My nitrogen has 4, it's not happy. And so what I'll do is I'll double up again. I'll take ones from my center atom and double up the bond. I'll take these 2 on the bottom of the C and I'll shove them in the bond. See, my carbon still has 8, but now my nitrogen has 6. Although we don't want 6, we want 8. So screw it, let's keep going. I'll grab the 2 on top of the C and also throw them in the bond. And when I do that, hydrogen has 2, C has 8, N has 8. There we go. There's the structure. One last one. Carbon dioxide. Carbon dioxide is made up of carbon and oxygen. Carbon is in family 4A, has 4 valence electrons. Oxygen is family 6A, has 6 valence electrons. There's 2 oxygens, each one brings 6. So I have 4 plus 12, or 16. Because 4 from carbon, 12 from the 2 oxygens. I'll take my C, it's underlined, put it in the middle, give it 8. I'll add my O's. Now, that was 8 electrons, I have 8 remaining. This one is tricky, and I'm doing this on purpose because it has a trick to it. By nature, most things are symmetrical. Things are balanced. You see, I have 8 electrons. If I start spreading them out, 1, 2, 3, 4, I could keep adding them to the guy on the left and make it happy. But when in doubt, try to balance things. I'll add 4 to the left, 4 to the right. When I do that, neither oxygen has 8. The one on the left has 6, the one on the right has 6. And so I'll say that carbon can double up. I'll take the electrons on the top of the carbon and give it to one of my oxygens. I'll take the electrons on the bottom of the carbon, give it to the other one of the oxygens. Draw my bonds as lines. There's carbon dioxide. Okay? My phone is exploding, so I'm taking it out of my pocket because it's bothering me. Ooh, that's not good. Okay? Now, this is for covalent bonds. That's how you draw them. I'm going to do other bits of complication with them for the next 20 minutes. But that is how you draw them. You will be drawing them on the homework. This is going to be a lot like the lens diagrams, and you're going to have to draw them on paper and upload pictures, and I'll grade them by hand, which sucks. So with these covalent bonds are once again equal sharing of electrons. There is such a thing, though, as a polar covalent bond. You see, sometimes when you share, it's not that even. You'd be like, yeah, we share this. It spends 90% of the time with you, and I only get it 10% of the time. That's sharing, right? A polar covalent bond is a covalent bond where the electrons are not shared equally. They spend more time with one atom than the other. The reason this happens is because some elements are more greedy for the electrons. They don't like to give it up. They really want them with them. This idea how greedy something is for electrons is called its electronegativity. And electronegativity follows the same periodic trends as non-metalness. Wow, my head is getting stuffed up as these allergies are getting worse with that window open. I should just close the window again. I'm losing the ability to think. The non-metallic character. It goes by the same trends. It is the highest electronegativity is to the right and up. And the higher the electronegativity, the greedier it is to share electrons. So it goes up when you move up, it goes up when you move right. It's of note that there's actually values for the electronegativity for each element. Even the metals have them. There's just set values. You don't need to know what the values are, just they exist. It's kind of a neat thing, though, that anytime you have any bond at all, you can find out exactly what type of bond it is by looking at the electronegativity values. That for any bond, if you find the electronegativity of both elements and just subtract the smaller value from the larger value, it'll tell you the type of bond. If the value is between 0 and 0.5, it's a non-polar covalent bond. If it's between 0.5 and 1.8, it's a polar covalent bond. And if it's greater than 1.8, it's an ionic bond. Really, in covalent bonds, non-polar covalent bonds are the more common. Non-polar covalent bonds are more common than covalent bonds, to be fair. But everything we did before this works the same. Now, it is an interesting thing about this. The unequal sharing of electron causes them to have a set charge, basically. It's known as a partial positive and a partial negative charge. Take, for example, hydrofluoric acid on the top here. Fluorine is a lot more electronegative than hydrogen. That means the electrons spend more time with hydrogen. If the electrons spend more time with, the electrons spend more time with fluorine. I misspoke. My head is just losing it. If my electrons spend more time with fluorine, what that means is that will be more negative. That means that'll act as if it has a negative charge. And if the electrons spend less time with the hydrogen, it'll act like it has a positive charge. This is common really with deltas and a plus and a minus, as I have in the upper right. Or sometimes it's drawn with an arrow with a plus sign and a line across, where the plus sign shows the positive side and the arrow points to the more negative. I won't be having you draw those on anything, but that is how they are done. Of note in general, anytime a molecule has one side that's more positive, one side more negative, we call it a polar molecule. And I already said the delta symbol sometimes represents this. The polar molecule just means that it has a positive side, it has a negative side. It will be affected by things like electricity because of this. And also, whether something's polar molecule or non-polar will have a lot of effect in solubility of things. It's why oil and vinegar don't mix, but water and vinegar does. But it's of note, it's more complicated than just are they polar or not polar because of is it a covalent or a non-covalent or polar. As soon as class ends, I'm taking allergy medication. It's a lot more complicated than just what type of bond is it? Is it a polar bond, a polar covalent bond, or a non-polar covalent bond? It also is affected by the shape. So we kind of got to get into the shapes. Now, before we get into the shapes, I said water is a polar. You can actually see that. If you statically charge a balloon and bring it near water, you can see that the water actually bends towards the charged balloon. That water reacts to charged objects. That's just because water is polar. Okay. What I want to talk about is the shapes. You see, when you make a molecule, when you make your dot diagram, when you make these things, once you have this formula, you can use that to find the shape, to find exactly what that molecule looks like. And the shape will be useful to work out, was it polar, is it non-polar as a molecule? There's something called the Vesper Theory, which stands for valence electron shell pair repulsion. And that's a fancy way of saying like charges repel. You see, electrons push away from each other. We learned that in Coulomb's law. And what it means is in a molecule, all of the electrons will move as far as possible away from each other. And these electrons trying to get the fuck away from each other will cause a shape. You can tell when I'm not feeling well when I co-smell. It'll show the arrangement of the atoms. That's what the molecular shape is. And it will just show the atom around the central atom. And will tell you whether you have it will tell you that if you have polar covalent bonds, whether or not the molecule will be polar or non-polar. Because you might have all polar covalent bonds, but have a non-polar molecule. This H2Be here is a non-polar molecule. Because of those polar bonds, they're pulling to either side, canceling each other out. And so you gotta know how to recognize the shapes. And so here's the shapes. We're only ever going to care about the center atom. And on the center atom, we are going to say how many bonded atoms. We don't care about type of bonds, just how many atoms are bonded in and how many lone pairs are on the center atom. Anytime the center atom has 4 bonded atoms and 0 lone pairs, that is called tetrahedral. And basically everything's going to be 109.5 degrees from each other because that is going to be the angle where everything is as far away as possible. If instead you have 3 bonded atoms and 1 lone pair, the same thing actually happens, the same shape, but one of those bonds is replaced. One of those bonds is replaced by just electrons, and that'll be triagonal pyramidal. Sometimes just called pyramidal, but triagonal pyramidal. That really the shape of this and this is just this. Why am I pointing? I'm pointing at a screen. You can't see me pointing. It's just the difference of that H. Oops. Nope. That. Come on. Look. That H being there or not, right? The electrons are still there, but whether or not the H is there. If instead you have 2 bonded atoms and 2 lone pairs, that is called bent. It is flat. It is the same general shape, but now only things on 2 of them. If you have 2 bonded atoms and 0 lone pairs, that is lineal. No, we only care about lone pairs on the center atom, because the furthest away they can be from each other is on opposite sides of the center. And if you have 3 bonded atoms and 0 lone pairs, that is trigonal planar, because it's going to be flat and they're making a triangle from each other, because that's as far away as they can get. Now, just listing those like that, it's going to be impossible to keep track of them. But this is the secret. Side note, this chart, you're going to need it for the final. This chart says if you draw the shape, this will tell you how many, if you know how many atoms are bonded onto the center atom and how many lone pairs are on the center atom, this will tell you the shape and will it be polar if it has only polar covalent bonds. Now, the polarity can get messed up if it is covalent bonds. I will always assume the bonds are polar covalent. You should too. Side note, if you try to skip this and just Google it because I'm making that assumption, you will get wrong answers and I will mark it as wrong. It's a good way to make sure you're going through the work. But this will tell you, once you draw it, what is the shape and is it polar if it has polar covalent bonds. How to use this is as follows. Let's say I draw water, and water was, let's say I draw sulfur trioxide, which we did earlier. That is what sulfur trioxide looked like. If I look at sulfur trioxide, I can say it has 3 oxygens stuck to it. That is 3 bonded atoms. And the sulfur has no lone pairs. Therefore, the shape of sulfur trioxide is trigonal planar, and this is non-polar. Make sense? Drawing, it's the hard part. Once you draw it, just look at the chart. Now I'll do water. Water was the example early on. That's the shape of water. I can say water has 2 bonded atoms. They're both hydrogen. And on the center atom, there is 2 lone pairs. 2 bonded atoms, 2 lone pairs, that is bent. And it is polar, which we already saw with that balloon picture. Does that make sense? Okay. That is the end of this chapter. So, don't forget, you have homework due tonight. You have your last lab due on Friday. Don't forget, I posted a survey that I'm going to hand in Thursday, which is the 29th, on when I'm going to do the review session. Your final is on Monday of finals week. We got one last chapter. And honestly, of the chemistry stuff, it's the most fun. Chemical reactions. We get to see shit light on file. But other than that, I'm going to leave you be unless there's any questions. We good? All right. I'm going to go pass out due to an overabundance of pollen in the air. Have a good night.